Hello everyone, and thank you for joining this webinar. My name is Meven Wiban, and I'm a coastal engineer at DHI Australia. And today we're going to talk about shoreline protection against erosion. During the previous webinar, we've had a look at we've been describing some of the main processes involved in sediment transport. And the idea of today's webinar is to look at how these processes can create erosion along the coast and detail how we can, or some of the methods that can be used to protect our coast against erosion. The previous webinar is still available online, so if you want to have a look at it, you're welcome, and it will probably help you understanding some of the processes. Last time we've had a look at the basics for sediment transport, and this is today's agenda for the webinar. So we'll start by trying to classify or see how we can classify the different the sandy coasts. Then we will look at the different types of erosion that can affect this coast, and then we will detail some of the main measures against erosion. And especially two types of measure. First, the protection that consist in hard structures, and the second one, which is a soft way of protecting the coast by using nourishments. Basically, when we wanna look at erosion, we try to define what we call a sediment budget, which helps us defining the areas where deposition and erosion occur. Here is an example of a coast where a harbor has been built. And we can see on these satellite images that due to the construction of this harbor, which blocks the sediment transport along the coast, we can see that on the southern end of the breakwaters, there is an accumulation of sand, and north of the harbor, there is erosion. This is due to the fact that the harbor blocks the sediment transport, which was originally oriented towards north. There are many tools that can be used to establish a sediment budget. For instance, satellite images. When we have a certain number of satellite images spread in time, we can have a look at where the coastline has retreated, and also we can sometimes relate this to developments along the coast. We can also use a bathymetry survey to identify accretion and erosion on the seabed, and sometimes even information from the authorities on maintenance dredging rates in the ports or in the navigation channels. And finally, we can also mention that numerical models can provide a good estimation of the sediment budget. But before looking at the erosion itself, let's look at the different coastlines that we have, and let's try to classify these coastlines. The erosion is not necessarily the same everywhere, and the action of the coastal processes on the geological setting in a specific area will result in the development of different types of coastal profiles and coastlines. There are different ways of classifying the coast. One of them is to classify the coastal profiles based on the wave conditions, the tidal regime, storm conditions, available sediments, or geological conditions in general. Another way of classifying is more like an engineering classification of the coastlines, which is more based on the morphological response of the coast when we intervene on it. In the end, the classification of the coastlines helps us understanding the main physical conditions that we're facing, and also defines which kind of shoreline management measures will be potentially applied to protect against erosion. One way of classifying the coast can be based on the exposure to the wave climate. This is a good example. This satellite picture here is from Cape Cod in the US, and we can see that these two neighboring beaches, which are separated by maybe 3 or 4 kilometers, have a completely different visual aspect. And this is mainly due to the exposure of the stretch of coast to the waves. On the east coast, there is a good exposure, and we can see that there is a beautiful wide sandy beach. And on the west coast, it's a more protected area. and therefore the beach is not as beautiful, and we can even see that there is some vegetation. So let's see how we use wave exposure to classify the coast here at DHI. Basically, we define three types of coast: the exposed coast, the moderately exposed coast, and the protected coast. And this is based on the significant wave height, which is exceeded 12 hours per year. When it's higher than 3 meters, we classify the coast as exposed. When it's between 1 and 3, it's defined as moderately exposed, and when it's below 1 meter, it's defined as protected. Now we will look at some examples where we illustrate this classification. These two pictures here show exposed or moderately exposed littoral coasts where there are abundant sediments and a limited supply of fine sediments. So we can recognize again the Cape Cod on the left picture, and we can see that thanks to the exposure of the coast to the waves, we have a nice, beautiful sandy beach. Typically, the annual gross sediment transport along this kind of coast is between 50,000 and can be up to 1 million or even more cubic meters per year. On the right picture, we can see a moderately exposed coast where there is still abundant sediments. And we can see that as there are limited action or less action from the waves, the beach is slightly narrower, and we can even see that there is some seaweed that is allowed to be deposited because it's not washed away by the waves. Here is a picture of another moderately exposed type of coast, which is typical from the tropical environments where there is monsoon seasons or heavily swell dominated wave climates. And this type of coast is characterized by persistent wave conditions, which will typically wash away the fine sediments, even though there can be some abundant supply of fines. Along this kind of coast here, we can see in Sri Lanka, we can have typical annual gross sediment transport of between 1,000 and 500,000 cubic meters per year. So this was for exposed and moderately exposed coasts. Now let's have a look at the protected coasts. This is typically seen in areas in connection with small bodies of water, such as estuaries or lagoons or fjords. It can also occur out of large bodies of water, but requires specific conditions, such as a very mild climate or very shallow area, which protects the shore against the wave action. Under these conditions, the beaches are relatively narrow and sometimes even non-existent, and there is usually an accumulation of fines which are often supplied from neighboring rivers. This can typically lead to marshy environments in temperate climates, or in mangrove vegetated zones and muddy coasts in more tropical areas. Another type of coast which is worth mentioning is tidal flats, where the tidal processes dominate over the wave processes. They are usually characterized by wide and gentle slopes of the foreshore, and we really often see a huge accumulation of fine sediments. In these areas, sediment transport processes are very complicated because of the influence of the tidal currents and waves. And there are also very often both cohesive and non-cohesive sediments that are involved, so it makes it even more complicated to understand. Let's finish with coral coasts. This type of coasts normally occur in the tropics, away from supply of sediment, where water is very, very clear, or typically in arid climates. Due to the presence of a reef in front of the beach, the waves are breaking, and therefore the wave action on the coast is very limited. And this often lead in very narrow protected beach, and which are difficult to access. It can still be interesting coast for fishermen, for instance, because Very often, some natural protected location can be used by the fishermen to moor their boats. Nature cannot be changed, so sometimes it's not possible. It's simply not possible to have a wide beach in a protected area. As we've seen in the different pictures before, the wave exposure provides good sandy beaches, whereas protected beaches develop into muddy beaches with vegetation. The structures along the coast can cause protected areas and enhance the tendency for muddy beaches. Here is an example in Denmark where there is a breakwater that has been constructed on the north of the coast, and the area just west of this structure develops in a non-attractive muddy beach. So one idea here to improve this situation would be to shorten the northern breakwater and give up the idea of having a good beach at the north, and then extend slightly the southern breakwater and nourish the beach in order to reduce the travel distance of the waves to the beach, in order to increase the wave exposure, and therefore guarantee a better beach quality and better sand quality on the beach. This requires some work in order to improve the situation. Another way of classifying the sandy coast is based on the coastal response it has to interferences. In that sense, wave direction is also a very important parameter. As we've seen during the previous webinar, you can still consult it online. The longshore sediment transport is dependent on the angle of incidence of the wave energy. So when we have waves arriving normal to the shoreline, the angle is close to zero, and therefore the longshore sediment transport is also close to zero. Then when the angle of incidence increases, we have an increase in sediment transport until it reaches about 45 degrees. And if the angle of incidence increases more, the waves will become more and more parallel to the coast, and therefore generate less and less sediment transport, or longshore sediment transport. And this is the starting point of Q alpha curves, but I will talk about that a bit later. Depending on the wave direction, we can therefore have stable or unstable coasts. The A section characterizes stable coastlines, which is on the left part of the slide. So in the typical case of a stable coastline, we have an incident wave that is arriving on the coast with an angle which is below 45 degrees with the shore normal. Instead of having a straight shoreline, let's imagine we have a small perturbation along the coast. What happens in the stable case on the A part of the curve, if the difference between the angle of incidence and the shore normal augments, then the sediment transport augments, which leads in the situation that is described here, where on the southern part of the perturbation, the sediment transport is lowered, and on the northern part, it's increased. And therefore, this leads to a reduction of the perturbation. Now, if we look at the unstable stretch of coast, which is in the B part of the curve, it is the opposite. When the difference between the angle of incidence and the shore normal augments, we have a decrease in sediment transport, in longshore sediment transport. And it's the opposite as what happens on a stable coast, which means that we will have an increase of sediment transport on the southern part and a reduction on the northern part. And this will lead to accumulation on the offshore part of this perturbation. So what we have to remember when we look at this curve is that when the angle of incidence is relatively small, so below 45 degrees more or less, we tend to have stable shorelines. And where we have very oblique waves, it usually leads to unstable coasts. This is an example where we have both situations at the same area. It's a stretch of coast in Malaysia, in Pulau Pinang, where we have typically northeast monsoon waves and a very silty water. We can see it's sort of brownish. At this location, there have been some nourishment that have been applied along the coast. What we can see on the western part of the picture is that the beach field is completely out of control due to a very oblique wave angle. And if we look a bit further to the east, we can see that we have a natural morphological stable beach due to a more moderate wave angle. And this leads to a good quality of beach, even though the water is relatively silty. And this is once again thanks to the wave exposure, which washes away the fine sediments from the beach. In this kind of situation where the nourishment on the western part of the beach is completely out of control, we can maybe imagine that a small structure would help stabilizing the nourishment, for instance. But this would require some studies and design. Let's get back to the Q alpha curves. It's a very important tool, so I'd rather spend a bit more time on it. What a Q alpha curve does is relating the shoreline orientation to an associated sediment transport, to a net and gross sediment transport. So this can be assessed by calculating for a certain number of orientation what would be the sediment transport for a specific wave climate. This is very useful to identify what is the equilibrium orientation of the coast, which is defined when the net transport is 0. It can also be used to assess the lifetime of a nourishment or to estimate the accumulation along a structure, for instance. Here is a schematic way of summarizing the two main parameters that we've been looking at. So the wave exposure and the angle between the shoreline normal and the wave incidence. And we typically define different coastal types based on these two parameters. I will not detail all of them, but if you want to have more details about these different types of coasts, I suggest that you have a look at the Shoreline Management Guidelines book, which is available on DHI's webpage. As we have seen in the previous webinar, there are different types of coastal processes which lead to different types of sediment transport, and this can lead to different types of erosion. The acute erosion is typically the flattening of the coastal profile due to offshore directed cross-shore sediment transport, and it's usually very episodic, event-related type of erosion. On the other hand, we have chronic erosion, which is typically connected to longshore sediment transport, and which consists in a general retreat of the entire coastal profile due to a gradient in longshore sediment transport. And then we can also mention intermittent erosion, which is due to fluctuations in wave climate and sediment supply. Let's start with acute erosion. As I've said before, the acute erosion is typically linked to storm events. Basically, what happens is that during the storm events, we have an erosion of the upper part of a profile, like erosion of the dunes or of the upper part of the beach. And this sand is deposited further offshore in the outer part of the profiles. This causes a flattening of the profile, which leads to erosion of the shoreline. What can happen is after a storm or severe storm event, calmer periods will tend to push back the sediment to the upper part of the profile. In the end, acute erosion and the subsequent accretion during the calm period is more or less a redistribution of the sand in the coastal profile. So it doesn't really remove sand from the profile, but it's moving it back and forth along the cross-shore direction. This is illustrated on profiles that have been measured in Australia, where on the upper part we have a profile that has been measured before and after a storm event. So we can see that the sand, all the sand that was located in the red area, has been pushed away in the offshore part of the profile due to cross-shore offshore directed sediment transport. And then during the following period, which was much more calm, so in the lower part of the graph, we can see that the sand that was located offshore in the red area has been, or some of the sand has been pushed towards the upper part of the profile. Chronic erosion is related to longshore sediment transport, and especially to gradients in the longshore sediment transport. This kind of erosion typically affects the entire active profile. One main difference with acute erosion, which is a redistribution of the sand in the profile, is that chronic erosion is usually not reversible. A typical example is in the lee side of a headland or a structure, for instance. As we can see here on this sketch, the waves are coming from northeast, and there is a headland, and south of it there is a beach. So we have longshore transport which is directed towards south, but the problem is that we have no supply of sand from the upstream location. Therefore, we have a gradient in the longshore transport, which is illustrated by the length of the arrow. Very close to the headland, there is very little sediment transport, and the more south we go, the larger the sediment transport is, and therefore the erosion occurs close to the headland. Very often during episodic storms or events, we can have both erosion occurring at the same time. The cross-shore erosion takes the sediments from the upper part of the profile to the outer profile, and at the same time, the longshore currents takes the sediment out of the section. If a shoreline is prone to chronic erosion, at some point in time, the shoreline will retreat to a point where the viability of the profile due to acute erosion is unacceptable. And therefore, it's important to have in mind that protecting against chronic erosion may prevent acute erosion becoming a problem. Let's have a look at how we can protect the coast against erosion. But before getting into the different types of protection that can be applied, let's have a look at small definitions. We define different types of protection. First, the coast protection, which is a measure aiming at protecting the coast against coastline retreat. Then we have the shore protection, which is a measure aiming at protecting the coast against erosion, but also preserving and restoring the shore and the dynamic coastal landscape. Finally, we have another type of protection we won't detail today, which is a sea defense, and which is a measure aiming at protecting the low-lying areas against flooding. The choice of the protection measure depends on a lot of parameters. First, what is the problem? Do we have coast or beach erosion? Do we have flooding? Then another very important parameter is what is the cause of the problem, and that's where understanding of the coastal processes becomes very important. Then it's important to have in mind what are the morphological conditions of the coast. So this is typically based on the classification that we've been looking at before. And then we also need to assess what's going to be the impact of the scheme or the selected scheme on the adjacent stretches of coast. It's well known that most of the protection schemes move the problem somewhere else. So we have to think about that when selecting a measure against erosion. What we will do today is to look at different types of measures. So we will distinguish hard structures, which consist in constructions on the coast or close to the coast. These type of protections are typically built to prevent against chronic erosion by reducing the longshore transport and cause local accumulation. And then we'll have a look at the soft solutions, so typically nourishments, which consist in adding an amount of sand along the coast where some sand have been lost by chronic or acute erosion. So let's start with the hard structures, and we will start with seawalls. So seawalls are by definition passive structures that separate land and water areas. Their role is to fix the location of the coastline, and it's a type of protection which is very often used in cities where space is very scarce. But one of the main characteristics of these seawalls is that they have to prevent erosion against very strong wave action and typically during storms. So it's usually designed to resist very strong forces. So that's why they can have different shape in order to absorb the wave energy. One of the benefits of this kind of seawall is that they can be combined with other activities and very often used for promenades in the cities. One of the drawbacks of this seawall is that there's still potentially chronic erosion that occur in the profile, so it needs to be monitored and sometimes repaired also when very strong events hit the seawall. And due to the fact that it can potentially block part of the active profile, it usually lead to or it can potentially lead to downstream erosion as well. Another type of hard structures which are very close to seawalls, but not exactly the same, are revetments. So it's a bit the same than seawalls. They protect against erosion and mainly acute erosion in the foot of a cliff or of a dike. But the main difference with a seawall is that they're not designed to protect against flooding. Once again, they can have different shapes to absorb the wave energy. And another thing that is important is that they can be buried if they are constructed as as a soft protection, including nourishment. By burying the revetment, we typically build an emergency protection into the dunes in case of very severe erosion that would be unexpected. Another type of structure is a groin. Groins have been used a lot in history and on a lot of coasts. So let's have a look at how it works. So by definition, a groin is a straight structure which is perpendicular to the shoreline, and it functions by blocking part of the littoral transport of the longshore transport. So it should cover the entire beach in order to keep working even during storm surge and very high waves. So this is also one of the drawbacks of the groins, is that it segments the beaches. By blocking longshore transport, the groins will work by accumulating sand in the updrift area, and as a consequence, it will cause downstream erosion. About the drawbacks, there are different drawbacks that are listed here in the table. The main one is downdrift erosion, which can be significant, and also the 2D effects it can have on the currents, because due to the blocking of the longshore current, it will generate eddies along the coast, which can be very, very dangerous for swimmers near the structure. When we want to design a groin, we have to look at the width of the littoral transport. Depending on the exposure of the coast to the forcing, waves and currents, the width of the littoral drift is defined. Then the obliqueness of the waves will decide the form of the accumulation, because if the groin is sufficiently long, the shoreline will tend to reach its equilibrium angle, which is, as we've seen in the Q alpha curve, defined by the wave angle. Then the groin dimension decide on the extent of the interference. This is valid for both sides. It will decide on the extent of the accumulation on the updrift part of the coast, and also the length of the stretch of coast, which is subject to erosion because of the structure. And then finally, the number of groins when they're used as part of a groin field. The number of groins will also decide on the length of the protected area. So here we have very simple simulations to illustrate what happens when a groin is constructed along a straight coast. So in the upper figure, we can see that there is no structure, and on the left part we have slightly oblique waves. So as we've seen before, this is typical from stable coasts. So we can see that there is very little movement of the shoreline during the simulation. And on the right part of the slide, we have very oblique waves, which is associated to an unstable coast, and therefore we can see that the shoreline is moving a lot. If the groin is long enough, the accumulation will tend to reach the equilibrium orientation. If it's not long enough, the sediment will start bypassing the structure. Then if we have very oblique waves, the problem is that this equilibrium orientation is relatively close to the shore normal, which will lead to a shorter stretch of coast protected by this accumulation. In the end, the groins are not so well suited for coasts where we have very oblique waves. Let's have a look at how it works when we have a groin field. So as we've seen, a single groin causes downstream erosion. And therefore, to extend the length of the protected area, we can construct several groins in a row. And when we do that, both the spacing and the length of the groins are important. So let's have a look at that. So when we have a groin field, the accumulation will start on the most updrift groin. So that's illustrated on the top two illustrations. Then if the groins are short enough, they will allow bypass. So before the bypass starts, the development of the coastline between the groin is similar whether it's short or long. But then when the bypass starts, it will start filling the gaps that are in between the groins. So that's an important thing to have in mind when deciding on the length of the groin. To conclude on the groins, the groins are less and less used today because it has significant drawbacks, and especially the downstream erosion, and also the dangerous currents created by the structure. On top of that, it obstructs the passage to the beach because it has to block the entire beach. And yeah, it's not a very beautiful element. However, if a project include groins, even nowadays, usually some filling will be applied in order to avoid the temporary erosion and therefore reduce the least side effect of the construction. Now we are going to have a look at another common structure to protect against erosion, which is a coastal parallel breakwater. A coastal parallel breakwater is a structure which is parallel to the coast, and it can be located inside or outside the surf zone. By protecting the coast and providing a special shelter for the waves, it will reduce the sediment transport capacity in the shelter and therefore cause accumulation. One of the interesting features of the coastal parallel breakwater is that it can also generate accumulation when the waves arrive normal to the coast. This is illustrated on the simulations in the bottom of the slide, where we can see that the wave field and the wave setup on both sides of the structure will generate circulation, which will tend to push sediments toward the lee side of the structure. But some of the problems are there are also some problems, such as very strong circulation once again, which can be an issue for the safety of the swimmers, and also the water quality and the accumulation of debris in the area. So let's have a look at how we design this kind of structure. And typically there are two main parameters we can play with. It's first the length of the breakwater, and the second parameter is how far from the coast it's located. And this will have different influence on the evolution of the coastline. So this is a sketch showing how these two parameters can affect the evolution of the shoreline. There are some other parameters that can influence the shape of the accumulation, but this provides a first estimate. Then when we use coastal parallel breakwaters, there are many possibilities. Some protection schemes often use multiple breakwater, and here we have an illustration of how this affects the coast. So if we have a singular long coastal breakwaters, we will have tombolos forming and natural-looking long sections of beach. And this consists in a good protection and provide good water quality. But the problem is that it creates permanent tombolos, and therefore the bypass is very, very small. Then if we use segmented breakwater or long coastal breakwaters, we will generate a small, stable pocket beaches, which consist in very good protection against erosion. The main problem here is that it's going to have a poor aesthetic appearance, and they will tend to have a poor quality of water and also trap a lot of debris. So, and finally, if we have segmented breakwaters of short coastal parallel breakwaters, these breakwaters will generate salients and therefore more naturally looking beaches, but with a poor view because there will be a lot of structures located not too far in the water. As it doesn't block the sediment transport too much, the erosion in the lee side is not as large as for tombolos. And also the water quality is better, and it also have a less tendency to trap debris. But it doesn't protect as much as tombolos because the accumulation is not as wide. In conclusion, the breakwaters are able to protect shoreline in more diversified and less harmful ways than the groins. Moreover, the breakwaters can trap sand on the coast with perpendicular wave approach, which is not the case for groins. So it has some advantages that the groins don't have. These variations aim at at mitigating the disadvantages of the breakwaters by optimizing the shape of the structure. So this is an example of variation where by curving the shape of the breakwater, we will limit the offshore loss of sand and the lee side erosion by increasing the bypass. A curved breakwater also eliminate the dangerous currents by reducing the amount of eddies. And in the case of an artificial headland or a reef, it has a better appearance. And also the dry area that is created can be useful and used for recreational purposes, for instance. These were the main hard structures. Let's now have a look at the nourishment. By definition, nourishment is done when we artificially replace a deficit in sediment budget by the corresponding volume of sand. So in the end, it's a relatively natural way to fight against erosion. But the problem is that the real cause of erosion is not eliminated, and therefore it will continue on the nourished area. So nourishments will typically need long-term maintenance. The success of a nourishment depends a lot on the type of sand that is used for nourishing. And we typically try to use sand for nourishments which is similar or slightly coarser than the natural sand. If the borough sand is finer, it will tend to form a flatter profile, and it will require a lot of sand to have a certain beach width. If the sand is coarser than the natural sand, then for the same beach width, it will reach the native profile much quicker. There are different ways of nourishing. These are illustrated here. So it can be land-based operation. It can be pumped from the shore. It can be dumped by some large barges, or it can be rainbowed from the sea. And there are also different areas that can be nourished. So as illustrated here, we can distinguish three types of nourishment. The backshore nourishment, which consists in the strengthening of the upper part of the profile to increase protection of the backshore against erosion and breaching during the storms. We can also have beach nourishment, which is typically used to increase the width of the recreational area. And we can also have a shore face nourishment, which results in strengthening of the outer part of the profile, usually on the sea side of the bar, which will typically lead to a strengthened profile and also contribute to the littoral budget. So as the cause of erosion is not treated, the sand will leave the area. So it's important to have an idea of the lifetime of the nourishment and how long it will take for the sand to leave the area. And knowing that will help defining the volume that will be placed. So this is an example of calculation that provides a first estimate of the nourishment volume. And it's based on the chronic erosion rate, which can be estimated by satellite images, for instance. Obviously, this is a first estimate. Because when the sand is placed, there will be some other rearrangement that will occur due to the action of the waves and the currents. Some other considerations to have are what is the material available. It's not necessarily the case that we'll have a suitable material available nearby. So that's also an important parameter to have in mind. Then what will be the shape of the nourishment? How is it going to be placed along the beach? All these are considerations that are important when designing and preparing a scheme based on nourishment. there are many ways to protect the coast. It's not necessarily easy to select the right one, and numerical models are a great tool for testing different type of mitigation measures and test what will be the effect on the shoreline. Here you have an example of a coast where we placed a groin in one case, shore parallel breakwater in the bottom, and nourishment in the third case. And we can see that the numerical model helps us identifying the shoreline response. So here we can see that on the groin, there is accumulation on one side and erosion on the other side. For the shore parallel breakwater, it's located in a way that a salient is formed, but very locally. In the third case, we have a nourishment that is placed and transported away from its original location, which means that we'll have to nourish again. So thank you very much. I hope this was a useful overview of the different types of protection schemes. If you have any questions, feel free to contact me. I'll spend a bit of time on answering the questions that have been asked during the presentation. The next webinar will be held in 2 weeks from now. It will be about the principles for designing coastal developments, like artificial beaches or harbors, and we will look at specific examples where these principles have been applied for real projects and where these developments have been made in a way to work with nature. So thank you very much and see you next time.